Hi, welcome to IBR SSO panel session. My name is Lingling Fan. I'm from University of South Florida. The title of this presentation is Modeling Interactions Among IBRs. First, I'd like to introduce everybody the Australia case. And this case is published by AEMO engineers in a Secret journal. And the figure basically shows the western Murray zone. There are lots of IBRs, and the system experiences 7 Hz oscillations. As we can see, this is the voltage measurement. We can see 7 Hz oscillations are there if every IBR or IBR are dispatched to 100% in the blue lines. When we turn off, when we undispatch, when we ramp down everybody by a certain percentage, we can still see oscillations. That's the orange line. Only when we turn off a couple of IBR, then we don't see the oscillation. So therefore, it is reasonable to judge there are a couple of oscillation modes of 7 Hz, and some are existing because of the IBR interactions. And in this paper, IBRs were classified as non-contributors, positive and negative contributors. So this is the real world need that we can show. You can see that interactions among IBRs have been observed. So in this presentation, we can also show a simulation study for 100% IBR penetration system to show interactions. The presentation is about how to carry out quick stability assessments when what we have are just black box models. And the solution is well known. Perhaps we can use measurement-based characterization to measure admittance or impedance. And we have used this in the past. But today we want to talk about how to scale them up to assemble IBRs, loads, and network into a network admittance. And furthermore, how can we identify which IBRs are the influence factors? Can we use something like model shape analysis in the previous conventional state space model analysis? And here we are going to talk about S-domain admittance-based mode shape analysis. This is a conventional approach that we are going to split the system as 2 components. For example, this approach has been mentioned by the Wind SSO Task Force report published last year called TR80. And the system will be split into 2 components. So left part is the wind farm, so right part is grid, is series compensated grid. And these 2 will be represented by 2 impedances or 2 admittances. So the circuit analysis problem will be converted to a control problem or feedback system. The loop gain is basically 1 impedance, 1 admittance multiply another impedance. And with that, we can conduct the frequency stability, frequency domain stability check. Furthermore, we can also conduct this eigenvalue check just by looking at the zeros of these 2 admittances. So the previous approach lacks scalability. When we have multiple IBR and more general network, what do? So this one is going to say, let's do a little bit larger network admittance. Let's multiple bus instead of just a single bus. And let's do eigenvalue and mode shape analysis to see if we can really say something about the network. So an example below is a 2-area 4-machine system that has been used to conduct inter-area oscillation analysis. And you can see for the network from bus 1, bus 2 buses, you can reduce to 4 bus system just by keeping these generator buses. And once we have this network admittance, we can attach the generator admittance, and we have a total Y bus network admittance. So the nodal voltage can be written as the inverse of the Y admittance multiplied the current injection. And this is a closed loop system. We can check the bus admittance. Bus admittance is 0 or the poles of the bus impedance matrix Z to find out the system eigenvalues. Okay, so the critical step is to obtain every IBR's admittance. And we can do this just by harmonic injection. Suppose we don't know wind farm, but we do have OEM models put in PSGAT. So we're going to build a measurement test bed like this one, connect the wind farm to a voltage source, and make sure it is operating in the desired operating condition that it will really operate this way. So the voltage will be controlled from DQ to ABC, and we're going to add a perturbation in the DQ frame, and the current will be measured and convert back to the DQ frame. So with that, we can do perturbation of the d-axis first and grab the current dq, so we get the first component, first column. And then we can perturb the q-axis by 10 Hz, for example, and measure the IDIQ and do FFT analysis. We grab the second component, second column. So with that, we can grab the entire 2x2 matrix of the entire frequency domain zone. And here is the example that we're going to show a 9-bus system with 3 IBRs. And this is the 100% IBR penetrated IEEE 9-bus system. It's in PSGAD, and the original testbed is built by Kenan of National Renewable Energy Lab, and this model has been posted in GitHub. What we have done is to slightly tune this model to make the outer control loop change a little bit and push up a 3 Hz oscillations. And in addition, this one will be measured. So there are 3 IBRs, 1 grid following converter, 2 grid forming converters. And for each of these IBRs, we are going to establish a measurement test bed and conduct a frequency scan. So a couple of challenging points is to mention, or the things to mention is that we will make sure the test bed's operating condition matches exactly with the IEEE 9-bus online system. For example, the P and Q at PCC bus at the PCC point should be exactly matched. In addition, the voltage magnitude should match, and voltage angle should be matching. So therefore, its entire test bed, the measurement is using a uniform, or the 3 measurement tests are using a uniform DQ frame. So with that, by the way, this DQ frame has a fixed frequency called omega naught and 377 radians per second. So that way, this way we were going to grab 3 IBR DQ domain admittance. And that is YDD, YDQ, YQD, YQQ for every IBR from 1 Hz to 100 Hz by doing these measurements. Once we have frequency domain measurement, we are also going to do vector fitting to convert the measurements to a transfer function. So this is a 3 transfer function and invalid transfer function matrix, S-domain matrix 2x2. And this one will be assembled, attached to the grid admittance matrix. And the grid admittance, we assume we know, we have the knowledge, and then we attach it on the diagonal component. We can reduce the entire grid from 9 node to 3 node, and it does not influence our result. You can see in the range of, we can see a 3 Hz dominant mode can be identified by both approaches, whether we reduce the network or not. Since our measurement is from 1 Hz to 100 Hz, so we were just looking at from 1 Hz to 100 Hz dominant, and there are a couple of modes are pretty questionable, but we can discard that because our measurement accuracy does not cover this frequency range. This 3 Hz oscillation mode, dominant mode, can be verified just by this EMG simulation. In EMG simulation, in PSGAD at 10 Hz, IBR3 is power order increase 0.1 per unit. So you can see oscillation come up, and the IBR1 can show is oscillating against IBR3 for the voltage measurement, current magnitude, frequency, power, and real power. You can always see IBR1 oscillating against IBR3. So in this mode, an inter-area oscillation mode, well, how can we say this? We just use mode shape analysis. If these 2 modes are against each other 180 degrees apart, we can just say this is oscillation mode. And that is previously all those how we identified the inter-area oscillation mode, not only just by looking at that, but also looking at the theoretical part of the eigenvector. Okay, so we're going to conduct a mode shape analysis. Now, how do we conduct a mode shape analysis? Well, of course, it is an eigenvector, but in this case, it's slightly different. We do not directly looking at the eigenvector associated with this lambda I. Instead, we have to go back to this nodal voltage equation and looking at the impedance matrix. And we're going to plug in these 3 Hz eigenvalues. So this 3 Hz eigenvalue, 3 Hz mode is the pole of this Z. And therefore, if we decompose Z, we can make sure the one of the eigenvalue called gamma should approach infinity. So therefore, for Z, we are going to conduct eigenvalue decomposition and to make it as a 3 component. And you can see that the gamma 1 is indeed very, very large compared to gamma 1. The rest can be ignored. Therefore, we can simplify this just like SVD. You keep the important part in this case for eigenvalue decomposition. You also keep the important part, just gamma 1 associated part. And the left one is a vector. This is the scalar, won't change, but this guy will change according to different buses. Okay, so we can compare for just check gamma 1's eigenvector called QC1 column and examine each component of QC1 and find out which basis voltage is more observable to this dominant eigenvalue. This way, we can definitely say this is the mode shape stuff. So here we extend the mode shape not only just to voltage, but also to different measurements, including voltage magnitude, current magnitude, power, real power, reactive power. And all these eigenvectors or mode shape just says the same story, that IBR1 is oscillating against IBR3. And this is exactly match the EMT simulations. Furthermore, for example, we can see they can have IBR1, IBR3 all have very comparable magnitudes, and they have oscillating 180 degree. For this current, you can even see that IBR3 is more dominant than IBR1, and it is reflected in the EMT simulation as well. So this set of analysis basically tells us, yes, we have identified the inter-area oscillation mode, and this mode, it is related to these two GFM converters. It should be IBR1 and IBR3. It has nothing to do IBR2. So this is a typo here. So the concluding remarks we have here is are including following. Yes, power grid now have more and more IBRs, and their modes and controls models and controls are proprietary information. These are the challenges. However, we be able to use admittance-based, measurement-based admittance eigenvalue analysis, and we foresee that perhaps this kind of tool can give us leverage to do more kind of eigenvalue analysis. And we can do lots of different stuff. And in addition to just do screening analysis, we can expand this admittance-based analysis to do mode shape or model analysis. And this mode shape analysis can help us to identify the influencing factor of a dominant mode. And in this case, we successfully identified a 3 Hz inter-area oscillation mode. Thank you.